Hi everyone. So today we're going to be looking at the next little section, and that is the types of solutions. So far with these examples that we've been going through, we've had only one solution. So you have x equals something, y equals something, z equals something. Yeah, so you can say one solution or a unique solution. However, there are cases where you can have infinitely many solutions, and there are cases where you can even have no solution. Okay, and that depends on the system that you're given. Okay, those that did the homework problem yesterday, the day before, would have seen that one of the questions actually had infinitely many solutions if you write it out properly. Okay, so let's have a look at this. Okay, so there are three possible types of solutions. Okay, and these depend on the system that you're given. So number one, you can have a unique solution. Okay, so this is one solution where x, y, and z have some value. You can have infinitely many solutions. Okay, so you have a whole family of solutions that satisfy those equations. And number three, you can even have no solution. In other words, there are no x, y, z that satisfy the system of equations. Okay, so before we get to the three variable examples, so the x, y, z, I just want to show you a couple of examples in 2D. Okay, so can everyone see the two lines here? It should be sharing. Can someone just give me a thumbs up if you can see that?
Yes, sir, we can see it.
Okay, cool. So for this first example, we have these two equations. So x plus y equals 2 and 2x minus 3y equals 7. So that's like a 2x2 system that I've given you. If you plot these two lines, here we see on the right-hand side here, they intersect at one point. Okay, this 2.6 and minus 0.6. So that means that this system has one unique solution, okay, where they intersect here. Okay, so in this case, there is a unique solution to the system. If we look at the next example, so in purple here, we've got x minus y equals 1 and 2x minus 2y equals 2. Okay, so they're two different lines. However, notice that we can plot the first line, it looks like this. If we plot the second line, it's actually on top of the first one. So if we change the color here, just put dotted line there. So you can see that the two lines are overlapping. So since they're overlapping, we're going to have infinitely many solutions. Because remember, a solution means that the lines intersect somewhere. These lines intersect everywhere along the two lines. Okay, so every point here is a valid solution. Okay, so we have infinitely many solutions. Okay, if we look at this last example here with these two lines, we see that they are parallel to each other. So if they're parallel, then they have no intersection. And if there's no intersection, that means there's no solution. Okay, so those are the three possible types of solutions that you can get. So there's these three cases. Okay, so this is for 2x2, just to illustrate the idea. If you had higher dimensional stuff like 3x3 or 4x4 systems, it gets a bit more difficult to draw. Okay, but we can still work with them. Okay, and I'll show you some of those examples now. Okay, so let's have a look at the 3x3 case, because that's the one that we're most interested in. Okay, so examples. Okay, so now this is going to be difficult to plot, right? If you want to plot these equations. However, using the augmented matrix, we can read off the type of solution. Okay, so let's look at example number 1. So let's say you have your system and you've done your row operations and you end up with this as your last step. So you get 1, 0, 0, 0, 1, 0, 0, 0, 1, and then A, B, C. Okay, so you got this as your last step. Remember, this is our goal, what we were aiming for. So if we write this out back in equation form, this means x equals A, y equals B, and z equals C. Okay, so I've just rewritten it as equation form. And notice that there's only one solution. Okay, x has a fixed value, y has a fixed value, and so does z. So we have a unique solution. Or you can say one solution. Okay, so this is the case that we've been dealing with so far, when there's only one solution. Okay, for case 2, we can look at an example here. So this is like the homework problem that you had. Let's say you end up with the following system as your last step. We have 1, 0, 0, A, 0, 1, 0, B, and 0, 0, 0, 0. Something like that. Notice that the last line is completely zeros. So in fact, that equation, the last row, the last equation, it doesn't tell us anything. Because if we write this out as a system, as an equation for the system, we get 0x plus 0y plus 0z is equal to 0. But that just means 0 equals 0. So it doesn't add anything to the system. So we could just remove it if we wanted to. So this equation doesn't add any information. So in fact, we could have just crossed that row out. We can't do anything with it. So in this case, we're left with 3 things. The first row says that x equals A. The second row says that y equals B. And what about z? Well, it doesn't say anything about z. So that means z can be any real number. Okay, because there's no restrictions on z in this case. Okay, so that means we get a different solution for every value of z. In other words, we can write our solutions as a, comma, b, comma, z, where z is any real number. Okay, so since we get a different solution for every value of z, we must have infinitely many solutions, because there's infinitely many values of z. So infinitely many solutions. Okay, one solution for every choice of z. Okay, and number 3, third example, you might get something that looks like this. So we have 1, 0, 0, 0, 1, 0, 0, 0, 0, and A, B, C. You might get something like that. Okay, so let's try and see what these solutions might be. So the first row says that x equals A. The second row says that y equals B. And the third row, if we write it out fully, says 0x plus 0y plus 0z is equal to C. right? That's just writing it out as the equation instead of a row. But the left-hand side is just 0. The right-hand side is C. Now, if C is non-zero, right, we're assuming it's non-zero here, how can you have 0 is equal to a non-zero value? This is a contradiction. Okay, you can use the little lightning bolt symbol to show that it's a contradiction. So if there's a contradiction, that means there's no solution to this. No solution. Okay, we can't have contradictions in our system, so that means there's no solution to the system. Okay, so that is when this last row looks something like this. So you have all zeros on this side and a non-zero value on the right-hand side of the line. So in that case, there's no solution. If the whole row was zeros, then you would have infinitely many solutions. Okay, so those are just a couple of examples that you should look out for. Okay, so if you do get something like this, then you know what kind of solution you have. Okay, are there any questions so far? Okay, we've got a few definitions to go through, and then we'll have a look at an example. Okay, so the first definition. Okay, so if the system has at least one solution, okay, so at least one solution is the same thing as saying a unique solution or infinitely many solutions. Okay, but there has to be at least one. Okay, so if the system has at least one solution, then we call the system consistent. Okay, so that's our first definition, consistent. So if the system has at least one solution, meaning a unique solution or infinitely many solutions, then we call the system consistent. Okay, definition 2. If the system has exactly one solution, then we call the system independent. Okay. And definition 3. If the system has infinitely many solutions, then we call the system dependent. Okay, so those are 3 definitions that you need to know. So the definition for consistent, independent, and dependent. Okay, and they all depend on what type of system you have. Okay, so given a system, you can work out what type of solution you're dealing with, and then the system comes with these labels here. So either consistent, independent, or dependent. Okay, are there any questions on these definitions? Okay, let's have a look at an example. Okay, so let's say we're given the system x minus 2y plus z is equal to 3. 2x minus 5y plus 6z is equal to 7. And 2x minus 3y minus 2z is equal to 5. Okay, so we're given the following system, and we want to classify the type of solution. Okay, so what type of solution are we dealing with? And then after that, can we say anything about the system? So is it consistent? Is it independent? Or is it dependent? Okay, so first we need to turn our system of equations into an augmented matrix so that we can do our row operations easier. Okay, so let's do that. So we've got the coefficients of x being 1, then the coefficients of y being minus 2, and the coefficients of z being 1. So we get 1 minus 2, 1. Okay, and then the constants after the equal sign, that's 3. Okay, we can do the same thing for the other two rows. So we get 2 minus 5, 6, and 7. 2 minus 3 minus 2, and 5. Okay, so that's our augmented matrix for the system. Okay, so let's do our row operations and see what kind of solution we're going to get. Okay, so we have 1 minus 2, 1, 2 minus 5, 6, 2 minus 3 minus 2, 3, 7, 5. Okay, so the first thing that we need to do is turn the first entry in the first row into a 1. Remember this first bit, that needs to be a 1. So it's already a 1, so that first step is done. The next thing to do is look at everything below, and those need to be zeros. So let's start off with the second row. How do we make that into a 0? Well, we can take row 2 and minus 2 times row 1. Okay, because then the 2 minus the 2, that will make it a 0, which is what we want. Okay, so let's do that. So we're going to get 1 minus 2, 1, and 3. First row stays the same. 2 minus 2, that's 0. Minus 5 minus minus 4, so that's minus 5 plus 4, that's going to be minus 1. And 6 minus 2, that's going to be 4. 7 minus 6, that's going to be 1. Okay, and we're only changing the second row. The third row can stay the same. So we have 2 minus 3 minus 2 and 5. Okay, so we've got the 1 and we've got the 0. We're almost done. So we still need this last entry here to be a 0. How can we do that? We can take row 3 and minus 2 times row 1. Okay, because then the 2 minus the 2, that's going to be a 0, which is what we want. Okay, so let's do that. Okay, so now the first two rows are going to stay the same. We haven't changed anything there. So we're going to get 1 minus 2, 1, and the 3, 0, minus 1, 4, and the 1. Okay, so now 2 minus 2, that's going to be 0, which is what we wanted. Minus 3 minus 4, so plus 4, that's going to give us a 1. Minus 2, that will be a minus 4. And 5 minus 6, that's going to be a minus 1. Okay, good. So we can see that the first column is 1, 0, 0, which is what we wanted. So that bit's done. So tick, that's done. Now we look at the second column. Okay, that's the one with y. The middle entry, we want that to be a 1. And the number above and the number below, we want those to both be zeros. Okay, so let's focus on the minus 1 first. So we need that to be a 1. How do we get from minus 1 to 1? We can multiply the row by minus 1. So minus 1 times row 2. Okay, so row 1 and row 3, they stay the same, so we can leave it as that. So we get 1 minus 2, 1, and the 3. We get 0, 1, minus 4, minus 1, 0, 1, minus 4, minus 1. Okay, good. So we got the 1 there. That's done. Next, the number above and the number below, they must be 0. Okay, so what can we do? Let's start with the number below, so the 1. So we can take row 3 and subtract row 2. Because then the 1 and the 1, they'll cancel. So row 3 minus row 2. Okay, that should get rid of that 1. Okay, so rows 1 and row 2, they stay the same. So we get 1 minus 2, 1, and 3. 0, 1, minus 4, minus 1, 0, 1 minus 1, that's 0, minus 4, minus 4, that's 0, minus 1, minus 1, that's also 0. So notice we've got an entire row of zeros. So that should look familiar. If we look back on the previous page here, we see that we're dealing with this second example here, where the last row is entirely zeros. So we should be getting infinitely many solutions if we carry on correctly. Okay, so just keep that in mind. When you get a row entirely of zeros, you should be looking for something like infinitely many solutions. Okay, so let's carry on, see what we can do. That bit's done, but we're not done yet. We still have this top number. We need that to be a 0. Okay, so we can take row 1 and add 2 times row 2, because then the minus 2 and the 2, they're going to cancel. Okay, so let's do that. Okay, so we're only changing row 1, row 2, and row 3, they stay the same. 1 plus 0, that's just going to be 1. Sorry, that's going to be 1. Minus 2 plus 2, that's going to be 0. 1 minus 8, that's going to be minus 7. And then 3 minus 4, that's going to be, so 3 minus 4, that'll be minus 1. Oh, sorry, not minus 4, minus 2, so that's going to be 1. So 3 minus 2, that's going to be 1. The second row, that stays the same, 0, 1, minus 4, minus 1, and 0, 0, 0, 0. Okay, so currently we've got the second column that's done. Okay, 0, 1, 0, that's what we wanted. Now for the last column, we can't really do anything. Okay, because we don't have, if this number here in yellow, if that was a 1, then we could eliminate those other ones there, but we can't do that, but that's fine. Because remember, we're not looking for a unique solution. We actually want infinitely many because that last row is all zeros. Okay, so that's fine. Let's rewrite this as a system of equations and see what we get. So the first row written out is going to be x minus 7z is equal to 1. The next row is going to be y minus 4z is equal to minus 1. And it says nothing about z, so that means z can be any real number. Again, there are no restrictions on z. Okay, it's free to be whatever it wants. So in fact, we could just call this a free variable. Okay, so if you have no restrictions, you're free. And it can have any value, so we can call it a free variable. Okay, you might see that term come up. Okay, so how can we write out these solutions? Well, we still want to try and solve for x. So x is going to be 1 plus 7z. Y is going to be minus 1 plus 4z. And z, again, that's free to be anything. Okay, so we get a whole family of solutions. We get 1 plus 7z for the x value, minus 1 plus 4z for the y value, and z for the z value. So for each value of z, we get a new solution. So if you put in z equals 0, you get a solution. Z equals 1, you get a solution. Z equals pi, you get another solution. Okay, so you get infinitely many solutions. Okay, so if you're looking in a different textbook or online, you might see some people do this, where they say, let t equals z. Okay, so they just do that so that you're not using z, which appears to be something like from the system. So, you have x, y, and z. Here, we're just renaming it. So this is just renaming. Okay, so then we can write the family of solutions. Okay, you can put it in like a set if you want, because it's a set of solutions. 1 plus 7t minus 1 plus 4 times t and t, where t is a real number. Okay, so you might see it written out like this as well. Okay, where it's a set of solutions or a family of solutions. Okay, so we know that there's infinitely many solutions. Okay, so if we go back to our definitions, here we go. If the system has at least one solution, a unique solution, or infinitely many, then we call the system consistent. Okay, so we know the system is consistent. Okay, and if we go back again here, if the system has infinitely many solutions, then we call the system dependent. So the system is consistent and dependent. Okay, so there are infinitely many solutions, which means the system is consistent and dependent. Okay, are there any questions so far? Okay, so it's not too bad. You just need to identify the 3 types of solutions. So unique solution, infinitely many, or no solution. So you can identify the type of solution, and then you can classify the system. So you can classify the system as consistent. Okay, if it has at least one solution, it's independent, if there's exactly one, and or it's dependent if there's infinitely many. Okay, so that is the classification system that we use. Okay, any questions? Okay, so that's enough for today. Tomorrow we can go through some more examples of this and more classification. Just before you go, please can you put your student numbers in the chat just so that I can take attendance. Okay, and then after this, I'll go through the formative quiz just to finalize the marks because I've seen a number of students weren't following the question there, because it said there, write your solutions in the form X, Y, Z, like that. Some students were just writing 2, 3, 4 like that with no brackets, which means the system didn't pick that up as a solution. And other people were writing X equals 2, Y equals 3, Z equals 4. And again, the online system couldn't pick that up as a solution either. Okay, so I'm just going to have to go and manually check those. Okay, so whatever mark you see now that's not finalized, I do need to go and manually check everyone's solutions now. Okay, but by the end of the day, you should have your finalized marks. Okay, I think that's everyone's student number there. Cool, thank you. Later on today, I will post the homework problems to the WhatsApp group so that you can try them out. Just another note on that, if you go on that homework submission part of that Learn 2022, if at the end of 5 o'clock your solution is not marked, that just means you weren't the first to submit. So remember, only the first person gets the bonus marks. Okay, so it's not that I haven't seen it, it's just that you weren't the first one to post. Okay, but if you do have any questions later on, please let me know on the WhatsApp group, or you can email me and then I can help you out. Okay, and remember that tutorial 1 is due at the end of this week. Okay, so it covers all the stuff from this week, and we will start next week with tutorial 2 with the tutors. Okay, so on Tuesday, 2 o'clock, we have our tutorial period, and then the tutors will go through the work. Okay. Yeah, so if you do have any questions, please let me know. Okay, bye everyone.